Hello, welcome to the second lecture in our series. In this lecture, we will be discussing for what problems we will be using machine learning and how to define a problem as a learning problem by using Tom Mitchell well-posed learning problem framework. Let us quickly recap what we discussed in the previous lecture. What is machine learning? Machine learning is about learning from data without explicit programming. Machine learning systems take data as an input and uh, gives model as an output. That model can be patterns or rules or function, and that model can be used for doing predictions or making decisions. You want the model, whatever the model that is developed, that should work well even on new or unseen data. And we had also seen the relationship between artificial intelligence, machine learning, and deep learning. Machine learning is a subfield of artificial intelligence, and deep learning is a subfield of machine learning, which uses artificial neural network. Now, the first question that we are addressing here is for what problems we use machine learning. For problems which writing explicit rules is easy and an efficient algorithm exists, for those problems, we are not going to use machine learning. For problems like multiplication of two numbers, we are not going to use machine learning. Checking whether a given number is prime number or not, we are not going to use machine learning. For problems like given an image, uh, finding whether image has a cat or a dog, writing explicit rules is not easy. And similarly, given a financial transactions, are there any fraud transactions? Writing explicit rules is not easy. For those problems, we will be using machine learning. Once after deciding that we are going to use a machine learning to solve a problem, how to define that problem as a learning problem? That's where Tom Mitchell has given a framework called well-posed learning problem. Now we will see the definition of the Tom Mitchell's of well-posed learning problem. A computer program is said to learn from experience E with respect to some class of task T and a performance measure P. If its performance at task in T as measured by P improves with experience. Briefly, when we will say that a machine learning a task, if it improves at a task with experience. So there are important components in the definition. Task, what the machine is trying to learn, that is a task. It could be learning to label uh, emails as a spam or not a spam. Experience, the data that is relevant to the task. And performance, it must be a quantifiable measure which tells you how well it has learned the task. And we will be discussing in detail these three tasks, first starting with uh, these three components. Starting with the task, what the machine is trying to learn. There are different types of tasks. So the first one is the classification. In the classification task, machine is expected to learn. Machine is expected to learn predicting a discrete label, saying yes or no, spam or not a spam, cat or a dog, or different types of diseases. It's like categorizing. And the next one is regression. In regression, uh, machine is expected to learn to predict a continuous numerical value. It could be predicting a house prices given some attributes and predicting a temperature, predicting a stock prices, or predicting a score in a cricket match. All these are like forecasting a number. And similarly, a clustering, grouping similar data points without prior labels. You are given a data without any prior labels to group similar data points. It's like grouping a customers based on their purchase behavior. You are given only transaction statements of all customers. You have to group them based on the similar behavior. So the next one is the translation. These are the different tasks, and next one is next component is performance measure. Uh, how well that it has learned the task. It must be quantifiable because if we cannot measure it, we cannot improve it. The examples of the measurements, we can take it as accuracy, the percentage of the correct predictions, like the number of correct predictions by total predictions into 100. That gives you the percentage of the correct predictions. Or in some cases, what happens is there is might be a class imbalance. If you take a spam or a not a spam, 99% of the mails are already known to be not a spam. Accuracy might not give you the correct performance measurement. We should use some other performance measures like precision, recall, or F1 score. These two are used in classification, and and the next is the mean squared error or R squared, which are used generally in regression tasks. So mean squared error is the average of the square difference between predicted and actual value. And next we have reward sum. If this is used in a reinforcement learning. It could be the total accumulated reward that agent receives for the actions. The next component is experience. Experience is data in the learning process. The learning process is decided based on what form of data that we are giving. So if you consider an analogy that we can consider, if the model is a student, the experience is textbook, lectures, and practice problems. So examples of experience, we can have a labeled data sets where uh, where the images are given as well as what is there in the image is also given. Like all the images where cat is there and with the label cat, all the images where dog is there, the label dog. So when label data is given, then we are going to use, we are going to say that as a supervised learning. So that means learning with the input output phase. Next, unsupervised learning, uh, where you have an unlabeled data is given, like the customer purchase data is given without defining groups. This, if this experience is used for learning, then this we call it as an unsupervised learning. The next one is the reinforcement learning, where in case of reinforcement learning, it is learning by trial and error, where the agent for every action it takes the feedback from the user. Based on the feedback, it learns. Okay, that is. And next, an important point here, the quality of experience influences the performance of the model. So now any well-posed learning problem should have these three components. What is the task? We have clearly defined what is the task that machine is trying to learn, and how can you say that it is improving with a quantifiable performance measurement P and an experience, the data that is used for learning the task. So that we call it as TPE, the three double TPE. Now let us consider some examples. Uh, the first example is chess learning program. The task here is machine is learning to play tennis. Machine is learning to play chess. The performance measure would be the percentage of games won against opponents. Experience is playing against itself. Our human opponents are analyzing recorded games. This is TPE and spam filter. Like machine is learning to classify mail as spam or not a spam. Performance measure can be accuracy or uh, or precision or recall, and experience is large set of emails labeled by humans as spam or not spam. So we have to consider it as a supervised learning. So these are the two examples, and any learning problem can be defined with these three tuples. TP. Okay, so why this definition is important? It gives you a clear structure. We can clearly articulate the problem to be solved, which also helps to track the progress, which also helps to compare two different approaches. The next step is uh, designing a learning problem. Design what are all the engineering decisions that we have to take um, when we want to solve this learning problem. What kind of functions that it has to learn and what kind of algorithm that we should use. This is what we'll discuss in the next video.